All right, folks, today we're going to do some more percent yield. We're doing problems 5 through 7. So the beauty of these problems right now is these take some thought. So if you're sitting here just thinking, I'm going to just plug something into an equation, you need to think a little bit, right? So we're trying to prepare 100 grams of silicon tetrafluoride by adding hydrofluoric acid to silicon dioxide. So we have silicon dioxide, and we're adding hydrofluoric acid to it. That's HF. And it is supposed to be producing silicon tetrafluoride, F4. SiF4G. What do you think? Does this look like a double replacement reaction to you? Yep, because the other product is definitely water. All right. So now to be able to balance this reaction, I've only got one oxygen on the right-hand side. So clearly I need to have two oxygens on the right-hand side, but that gives me 4 H's. That means I have to have a 4 here, and that gives me 4 F's. So I look like I'm now balanced. Right. The key here is that the percent yield of this process is 75%. So we already know we don't get 100% of what we want. So how in the world do we figure out how much we should get? Well, we want to produce 100 grams of this. But clearly, if our process is only 75% efficient, we need to try to produce more than 100. But how much more than 100? How do we figure that out? Well, if you think about this for a minute, you know that percent yield is equal to your actual over your expected times 100%. All right, so what's our question? Well, we know what we want to get. That would be our actual amount that we want to get. But we have to figure out how to make more than that, which would be our expected amount, and we have a 75% yield. So think about how you could plug that in, because we have to solve for expected. So how in the world do you get expected all alone on one side of the equation? Pause the video, see if you can figure out how to do that. All right, it's actually very easy. If you just go and multiply both sides by expected and divide both sides by percent yield, then you end up with this equation. Expected is equal to actual divided by percent yield times 100%. So let's see what that gives us. Your expected is what we don't know. That's what we're trying to calculate. And our actual, we know, is 100 grams. And we know that our percent yield is 75%. We're going to multiply by 100%. And that will give us 133.3 repeating grams. And that is how much silicon tetrafluoride we have to try to produce. So let's go and figure that out. We have 133.3 grams of silicon tetrafluoride, which is what we're trying to produce. Well, we have to get rid of grams of silicon tetrafluoride and go to moles of silicon tetrafluoride. Now, what are we trying to find out here? It says how many grams of hydrofluoric acid do we need to react? So we have to work our way back to hydrofluoric acid from where we are. So we have to get rid of moles of silicon tetrafluoride and go to moles of hydrofluoric acid. And then what we have to do is we have to go to, it says how many grams of hydrofluoric acid, so we have to go from moles of hydrofluoric acid to grams of hydrofluoric acid. All right, so let's go and put some numbers in. 1 mole of silicon fluoride to some number of grams. We have to figure out how much silicon fluoride weighs. And if we actually look up silicon fluoride, on the periodic table and do some work, we will come out with 104.078 grams per mole. Now, our silicon fluoride has a 1 implied in front of it, and our hydrofluoric acid has a 4. So that's a 1 to 4. And then we have to go to grams of HF. Well, 1 mole of HF, we have to figure out how many grams that is, and that's 20.006. You can pull that off your periodic table, do a little bit of work. Okay. And then what we do is we just multiply everything on the top, divide by everything on the bottom, and we get 102 grams. Actually, I think it's 102.5 grams of HF. Okay. Hopefully that helps. Number 6 is also a little bit complicated. Again, it's one of those things you have to think about. So, when gunpowder explodes, potassium nitrate, well, that's KNO3, plus carbon, that's C, plus sulfur, that's S, react with each other to form nitrogen gas, N2, plus carbon dioxide gas, CO2, plus solid potassium sulfide, which is Ks. All right, so let's see what doesn't balance. Well, our O's don't balance. You'll notice we have a 3 and a 2 over there. So we have to put a 3 in front of here and a 2 in front of here, which means we have 2 potassiums, which puts a 2 there. We have 2 sulfurs, which puts a 2 in front of there. We have 3 carbons, which puts a 3 in front of there. We're not even going to worry. Let's see, the oxygens are 6, the potassiums are 2, the carbons are 3, and the sulfurs are 2. So everything looks like it finally balances. Right? And this is where it gets fun. It says, if the original mixture contains 50 grams of potassium nitrate, so we have 50 grams of this. And by the way, KNO3, we figured out in the past that KNO3 weighs 101.102 grams. All right. So now, what in the world do we do? It's asking us the total volume of the gases. Volume gases, I'm so confused. Well, if you think about this for a moment, nitrogen is a gas. Carbon dioxide is a gas. Ks is not a gas. Right? So it's not a gas. So we look at these gases and we say, well, how do we do that? We have to combine them, but that's okay, because all gases, no matter what they are, if they're at standard temperature and pressure and they're a gas, then they take, each one takes up 22.4 moles. 22.4 grams, sorry, try it again, 22.4 liters for every mole. It doesn't matter what the gas is. The gases can be mixed. Air is a perfect example of a mixture of gases where this works. 22.4 liters in 1 mole. All right. So, but what do we notice over here about gases? Well, N2 is a gas, and carbon dioxide is a gas. And potassium sulfide is not a gas. So I'm going to have a total of 4 moles of gases over here. So let's see how this thing works. We'll start with 50 grams of KNO3. Now we're trying to convert from grams of KNO3 to moles of KNO3. And from moles of KNO3, we can go to moles of, do we go to nitrogen? Do we go to carbon dioxide? What do we do? Well, the concept is it doesn't matter. We go to moles of gas, right? Moles of gas in general, of all of the gases that are up there all together. Right? And then we go from moles of gas to liters of gas. So, let's see what happens. We have 1 mole of KNO3, and we know that weighs 101.102 grams. And our moles of KNO3 have a 2 in front of them. And our moles of gas, well, again, if we combine the nitrogen and the carbon dioxide together, we end up with 4 moles of gas. 1 of them is nitrogen, and 3 of them are carbon dioxide. That's the leap of faith you have to make here. That's the biggie. Okay? Then what you say is, well, how much space does 1 mole of gas take? Well, 1 mole of gas takes 22.4 liters. All right. So now what you should do is go ahead and work through the math and multiply it out and divide it out, and you get 22.2 liters of gas. Now that's not specifically nitrogen, it's not specifically carbon dioxide, it's a mixture of the two, but because they're gases at standard temperature and pressure, it doesn't matter what the gas is. It's always going to behave the same. So, well, how much did we produce? Well, we were told at the beginning that it produced 20 liters, but we're expecting 22.2 liters. So we multiply by 100, and we come up with an answer. Okay, and this particular answer is going to be 90%. So we had a 90% yield on our reaction. That's pretty good. Means most everything was captured that was burned. All right, let's do our last one for this worksheet. We have very hot zinc reacting with steam. What's steam? What's the formula for steam? Of course, it's just water. It's just hot water. And it will form zinc oxide, ZnO, with +2 -2, and hydrogen gas. And remember that hydrogen is a Brinkel-Huff element, so it's diatomic. Okay, if I look back at my equation is balanced, so I don't have to do anything to balance it. And it says that we have 5.4 liters of hydrogen that was produced when 20 grams of zinc was completely consumed. Okay, so our key here is 20 grams of zinc. So we have 20 grams of zinc. And we have some number of liters, 5.4 liters of hydrogen gas. Okay, so let's go ahead and do this one. We're starting with 20 grams of zinc. And we're going down to, it's actually 20.0, which gives us 3 sig figs, which is nice. We have to look at how much zinc weighs, grams of zinc, and moles of zinc, and then moles of what we start with, which is zinc, and moles of what we're targeting, which is H2. And then we have to go from moles of H2 to, let's see, what we're trying to do, we're trying to go to liters, because it's talking here about liters of H2. We're going to liters of H2. All right. Well, we know that 1 mole of zinc weighs, well, we got to look that one up. Okay, and that's 65.39 grams per mole. Now, we have no coefficient in front of zinc, and we have none in front of hydrogen, so that's a 1-to-1. And moles of hydrogen gas, well, how much room do they take up? Well, they take up 22.4 liters at STP. All right, so we've done that. So we do our math, and we come up with 6.85. 6.85, there's my pointer, 6.85 is what we expect to get. Right, well, that's not what we got. Right, we got 5.4 liters. So 5.4 divided by 6.85 will give us, oh, I have to multiply by 100%, and that gives us 79%. All right, I think that's it for this worksheet. If you have questions, please see us in class. We'll be more than happy